Hello, this is Lazarus at Telecom Tech, where telecom and networking technologies are simply explained. Today, we'll be simply explaining Classful IP addressing. Now, if you like what you see in my videos, please take a moment to subscribe so you can get updates to newly published content. And if you do like this video, please click that thumbs up button. When I was first learning about IP networks, the idea of classful and classless addressing was not very clear to me. Hopefully it won't be the same for you, because in this video, I'll be examining classful IP addressing. I'll simply explain it now in a way that I wish I was taught when I was learning way back when. In an upcoming video, I will also address classless IP addressing, so look forward to that. Now, when IPv4 was designed in the early 1980s, most host devices were very simple terminals with limited capabilities. IP network addressing was supposed to be a very simple process of just putting in the 32-bit address. No fields for subnet mask and other network parameters were even conceived. For this reason, the designers of IPv4 decided to include in the design a hardwired subnet mask. This hardwired mask simply stated that IP addresses in a particular range will always get the same subnet mask. Said in a different way, IP addresses in a particular class will always get the same subnet mask. So IPv4 addresses were separated into 5 classes. We have Class A, Class B, Class C, D, and E. These classes were defined based on their leading bits. Now remember, network devices see IP addresses in binary. So that's what we need to examine now to further understand this concept. So by definition, the leading bits of each class are as follows. Class A always starts with a bit of 0. Class B always starts with 10. Class C always starts with 110. Class D always starts with 1110. And Class E always starts with 1111. Now, classes A, B, and C are the classes that are used for general IP addressing. Class D is reserved for multicast addresses, and Class E was initially reserved for future use, experimental use, and for research, and as of yet, they still are not in use for general networking purposes. So for the rest of this video, we'll be talking about IP addresses that belong to classes A, B, and C. The other 2 classes will be covered in another video. Now let's take a look at the ranges of IP addresses that each class contains. Remember, IPv4 addresses are 32-bit numbers. So let's start by looking at them in that context. Class A IP addresses in binary look like this, where we have an initial 0, and all the X's you see there can be either 1 or 0. So that means that the Class A address range is from all zeros to 0 and then 31 ones. So what does that look like in the more familiar dotted decimal format? It's a range from 0.0.0.0 to 127.255.255.255. So any address in that range is predefined as Class A. Let's look at the other 2 classes in a similar fashion. Class B IP addresses in binary look like this, where we have 10 and then the rest of the bits are set to either 1 or 0. That means that Class B addresses can range from 10 and 30 zeros all the way to 10 and 30 ones. What does that look like in the more familiar dotted decimal format? That's a range between 128.0.0.0 to 191.255.255.255. So any address in that range is predefined as a Class B address. Let's go on to Class C. Now, a Class C address in binary looks like this. It starts with a 110, and then the other 29 bits are set to either a 1 or a 0. That means that Class C addresses range from 110 and then 29 zeros all the way up to 110 and then 29 ones. Again, what does that look like in the dotted decimal format? That's a range from 192.0.0.0 all the way to 223.255.255.255. So any address in that range is predefined as a Class C address. So let's take a look at a summary of all of this. The Class A range can be seen here, Class B we can see here, and Class C is set to that range. Now the advantage of a classful address is that when you configure it on a device, you simply configure the address. No subnet mask needs to be configured. In fact, you don't have to configure anything else. Now, this may seem like a small benefit, but at the time, when even the least bit of innovation in computing was costly, reducing even the number of fields you need to fill out on a terminal to configure the network parameters of a device was of benefit. So addresses of each class had a predefined subnet mask. If you configured a device to be in a Class B address range, then the subnet mask was automatically configured for you internally to the device. It was part of the protocol itself. So what are those predefined subnet masks? Well, here they are. Any Class A address will automatically have a subnet mask of 255.0.0.0. Any Class B address would automatically have a subnet mask of 255.255.0.0. And any Class C address would automatically have a subnet mask of 255.255.255.0. Now, why were these specific subnet masks chosen? Well, it was really a matter of convenience. The dotted decimal format had dots between octets, so why not just set the subnet masks to match up with those dots? Devices couldn't care less what subnet mask you would use, but for humans, this way they can be written out much more easily. So a terminal that was assigned an address of 135.15.25.3, for example, was automatically internally assigned a subnet mask of 255.255.0.0, since it was a Class B address. Similarly, an address of 199.1.187.35 is assigned a subnet mask of 255.255.255.0 without any additional configuration parameters. Now, someone may say, and they would say this correctly, isn't this inefficient? Of course. Class A addresses with a subnet mask of 255.0.0.0 will only allow us to have 128 networks in the whole world. And each network will have 16 million hosts. That doesn't make sense. Well, remember that in the early 80s, there were at most several hundred hosts in total on the internet of the time, so efficiency was not really a concern. Ease of implementation was more important. So these inefficiencies caught up with the protocol, and this classful system proved to be too restrictive. For this reason, classless IPv4 addressing was introduced in the early 1990s, and I'll talk about that in another video, which is coming soon. Now, even though classful addressing is considered obsolete, it still remains as a functional part of many of today's modern network equipment and devices. For instance, on the command line interface of a Cisco device, if you issue a command with just the IP address without a subnet mask, it will often assume the classful subnet mask. For example, when configuring EIGRP, the router will function in a classful way. If you issue the network 20.0.0.0 command, it accepts it without a subnet mask, and it will assume the 255.0.0.0 subnet mask since the address is a Class A address. Now, just to be very clear, classful addressing for IPv4 should not be implemented today. You should always use classless addressing for a more efficient usage of the available address space. However, it's good to know what classful addressing is and why it existed in order to more fully understand how we use classless addressing today. Watch out for my next video on classless IPv4 addressing for more information. I hope you found this video useful, and if you have, please do click that thumbs up button. If you'd like me to address other related topics, feel free to let me know in the comments, and please subscribe to get updates to newly published videos. I'm Lazarus at Telecom Tech. I hope this has been helpful for you, and I'd like to thank you for watching.